The next speaker is Draguna Vrabie. Draguna is a chief scientist at PNNL. She works in the area at the intersection of control system theory and machine learning, and her work focuses on designing of adaptive decision and control systems. And today she will be talking about deep learning for mobile predictive control.
I'm going to talk about the integration between deep learning and model predictive control, which we believe at PNNL that is an opportunity to enable integration of all of this automation to a broad spectrum of applications that currently do not take advantage of automation, such as the agriculture, precision agriculture, robotics that was just presented. This is work done in collaboration with a number of people from PNNL, and I would like to start by first motivating why we're doing this. For those who are not deep into control systems theory, here is a very high-level introduction of model predictive control. Basically, in control system technology, in engineering, 95% of the process control loops are very simple proportional integral derivative loops. These are single input, single output. They work. They are, however, suboptimal. And for the the remaining 5% of the control loops, those that matter, those are who are the money-making loops. In industry, model-based predictive control is the technique that is currently being utilized. And model-based predictive control is something that is a control technique that utilizes models, utilizes prediction, combines models in a predictive optimization framework to compute over a prediction horizon optimal decisions. And this is being done over and over iteratively as time passes on. So therefore, model-based predictive control is a very promising technique that can optimize behavior of dynamical systems. Why do we want to integrate deep learning with optimization-based control, such as MPC? First, because, as I mentioned, these techniques use models. So in order to apply them, you need to spend a large amount of effort to identify these models and to formulate them mathematically, to implement them so that you can solve these optimization problems. So this is a very time-consuming step. The second issue is that when you implement optimization-based techniques, it is often challenging to explain the decisions, the optimal decisions that are being computed by these optimization-based controllers. And we believe that deep learning can also facilitate translation between these computed decision sequences and something that a human would understand. Basically would help us answer the question why. Why do you recommend this control decision? And then lastly, but not least important, is that integrating deep learning with optimization-based control allows these systems to be continuously adaptive and not just optimal. And this would enable continuous learning in these control and automation systems. So the first thing that we asked was, well, can we even use deep learning to deep learning models to capture the decisions that an optimization-based controller would make? So in this case, we looked first at imitation learning, and we tried to train a deep learning model to replicate or to to imitate the decisions made by an optimization-based controller. What I'm showing here on the slide is a result that we obtained using an application in energy efficiency for building energy. And what we've shown is that, yes, this is possible. And not only it's possible, but it also allows implementation of advanced control methods with less need for computing resources, CPU time, memory, and with almost no cost in terms of software that will be utilized in real time for real-time computation. This work just was awarded last week, Best Paper Award in a Dynamical Systems and Control conference. So this gave us some confidence that we can use deep learning models to implement optimization-based control decisions. But the challenge was identifying the dynamics of the system that we are going to control. So this slide is just highlighting both challenges with pure physics-based modeling, as well as purely data-driven approaches for capturing the dynamics of complex systems. And our approach was to not pick one or the other, so move away from purely physics-based, and also not do purely data-driven methods, but instead combine these methods into machine learning-based approaches that use deep learning models, but inject domain knowledge in these deep learning models. So here's an approach that uses block-structured neural state space models for dynamical systems. So often dynamical systems are represented as state space dynamic representations. And what we've done here was to capture that representation into the deep learning structures of our models that will later on be trained using data. This allows us to incorporate this physical knowledge that is well understood in many systems, and allows us to train these models using data captured from the domain. Here are some examples of neural state space models that articulate the variety and diversity of these models and generality of the models that we are using. And in different cases, we can specify what is the type of map that needs to be selected for different blocks in these block-structured neural state space models. And also what is their equivalent type of nonlinear or linear system dynamics. And ultimately, training these neural state space model representations ends up being an optimization problem, where based on system measurements, you train the parameters of the neural network representations in those block structures to optimize the end-step prediction horizon mean squared error. This is great, and it's a great start. However, I haven't mentioned anything about constraints. The advantage of the approach that we are currently using is that in addition to training this neural network models that have been structured to capture nonlinear dynamics, we can also incorporate constraints that are known from physics, and these can be incorporated as specifications of functions that will later on be integrated or included in the objective function of the deep learning model training, basically in the loss function. What we've done so far was use bounds on inputs bounds on outputs. So we have ways to account for those known constraints, as well as the ability to reject any sort of random features that a neural net, that a pure black box neural network might be learning, and improve the generalizability of the model outside the training set using these predicted state smoothing losses. So overall, when you integrate all of these loss function elements into the overall loss for the training of the deep learning model, you are able to minimize the prediction mean squared error over this n-step prediction horizon. You're able to integrate all of these regularization knowledge for inputs, for outputs. You're able to smoothen the states. And this is just an example of a very simple four-state system where only the fourth state is measured. And it shows the comparison between some results that we obtained with this method, as well as results obtained when we captured these dynamics of the system. We try to capture the dynamics of the system using more traditional black box deep learning approximations. So far, we have the ability to learn these nonlinear block state space models with very good performance. We have a couple of publications that are available. And the next step is to use these models in a predictive control formulation. And what we're doing is first to observe the structural equivalence between traditional model-based predictive control implementations, basically solving this optimization problem subject to constraints defined by the dynamics of the system, dynamics which are often learned from physics or represented as purely physics-based models. There is a structure equivalent to formulating this problem as a training problem for deep learning models. So here what we have is the deep learning model that captures the nonlinear dynamics, as well as the deep learning model that represents the control policy. So this way we bring the two pieces that I described in the beginning together. So the learning of the MPC policy and the learning of the dynamics of the system together in a single end-to-end optimization problem. And because these dynamics are formulated to capture some of the physical knowledge about the system dynamics, we are able to train these controllers and learn simultaneously the dynamics of the system with much less data. We have a publication that shows, a very didactic publication that shows how this performs on a linear system. So we're going back to the origins, linear systems, everything is known over there. And here is an example result that shows for a particular linear system how the controller that is learned online from this data is able to maintain the state of the system within bounds. It's able to ensure that the state of the system is tracking the reference, that is this blue dotted line that sometimes goes outside the bounds, right? It's able to also make these decisions under uncertainty. And you can see here the uncertainty ranges and basically the control action that the controller is computing. And you see the comparison between what has been used as a training data set, the results that have been obtained for a training data set, the results that have been obtained for the validation set, as well as the test set, which is data that the controller has not seen before. And on the right-hand side, we are comparing the performance of these controllers that has been trained from data with performance of many other types of controllers, including 3 types of model predictive control. Traditional state space based state feedback controllers like LQR and linear quadratic integrator, as well as 3 implementations of reinforcement learning. And what we've seen is that the deep learning based MPC approach actually outperforms all the different methods because it brings together some physics knowledge as well as the power of deep learning to capture this approximate optimal control policy and satisfies the constraints that have been imposed. Current work includes extension of what I've described, including looking at architecture discovery, so moving beyond us selecting different block structures, but having that process more automated. Control for nonlinear systems, so testing of this approach for nonlinear systems and looking at its performance, as well as demonstration of this approach using real data and demonstration on embedded hardware. As well as extension to other types of dynamics. So what we've seen is that it works really well for ordinary differential equation type systems. We would like to explore extension to partial differential equations, differential algebraic equations, hybrid systems, and so on, so that we expand this applicability. In addition to this, within the research group, we're looking not only at control design and learning neural models, but also we're looking at integrating deep learning with traditional optimization solvers. We're looking at using deep learning and more generic machine learning methods to concurrently design the system and the controller to enhance the performance, the ultimate performance that can be obtained, as well as using learning to obtain deception robust controllers, because control systems are basically cyber physical systems. They are very susceptible right now to cyber attacks. So we would like to ensure that these methods that we are developing are not only very successful at optimizing performance, but also are resilient and robust to attacks of all different kinds, to all sorts of uncertainty, including cyber attacks. All of these activities have different sources of funding, and on this, I think, last slide, I want to acknowledge not only the team that has developed the work that I just presented, but also the broader team that I'm working with for all of these projects I mentioned, as well as the sources of funding that are supporting this work. So most importantly, the Mathematics for Artificial Reasoning and Science, the MARS initiative at PNNL, as well as the Data Model Convergence Initiative, which is looking at computationally efficient ways for implementing these methods in scalable ways and addressing larger scale and more complex system dynamics, as well as the Department of Energy, who is funding some of the work that I mentioned at the end, but I wasn't able to go deep into. With that, I'll pause for questions.
Thank you very much, Draguna, for this excellent presentation. I could hear this all night long. There are so very many things that are of interest, and I hope there will be people that would share the same opinion and would probably reach out to you. And so let me stop here, and congratulations on the Best Paper Award. And we heard it right from, it was a fresh news. And so I wanted to convey that congratulations from one of the chat sessions.